In this video, we will again look at two examples. This time our examples are given to us as a table of data. And so we want to take from this video, what are we looking for when we identify data as linear or exponential? So the first one says, during the log phase of bacterial growth curve, the following data was gathered from the bacterium Lactobacillus acidophilus growing in milk. Model the total amount of these bacteria cells. So when I'm looking at data, I want to look at how it is changing. So looking at these two, I can actually do the math here in my head. From 10 to 16, this data would have went up by 6. And then I go from 16 to 26, and right here, this data would have went up by 10. Now, when I look at how this data, which is the second column here, which is the Y data, is changing, I also need to take note of how the X data is changing. Here, this is a change of 1, and here, this is also a change of 1. So I can see from just doing that much work that it is not a constant rate of change. So not a constant rate of change. If the X's went up by 1 and the Y's went up by 6 every time, that would be constant, but that is not the case. And so because the change is not constant, that means that it is not linear. And so since our only other option is exponential, we are going to conclude that this must be exponential. Now, for exponential, we are expecting a constant percent. And so in order to find percent change, we do new minus old divided by old. And normally we do times 100, but we know that the formula actually wants the decimal, so we will not multiply by 100. So this percent change is the change in the Y value that we're looking at. And so here, this is going to be our old one as our initial one, and this is our new value an hour later. So plugging those two in, I have 16 minus 10 divided by 10, and so that gives me 6 over 10, which is the decimal 0.6. And so then the next thing that I need to do is to check, does that hold out with the rest of the data? Is it truly a constant percent? So I'm going to pick the last two here, and truly any other two would work. So I'm going to use this as my old value and the 66 as my new value, and I'm going to check it out. So 66 minus 41 divided by 41. And so I do this on my calculator. 66 minus 41 is 25 over 41, and dividing that out is, and it's not exactly, but it's very, very close, so it's 0.60, so 0.6. And so this percent is constant. And having a constant percent is verification that it is indeed exponential. Boy, I can't even spell exponential. Take a T out of there. There we go. So I'm going to use the formula that we've had in our notes, and that formula is that Y equals P 1 plus R to the T power. P is always the starting amount, so in this case, Y equals 10, the starting amount of bacteria at time 0. Inside our parentheses, I have 1 plus 0.6. My decimal here is positive. That's the first we've had a positive. But when I did the new minus old, I got a positive. So that's what I plug in to the T power. And then like we've done at other times, I'll go up here across the top of my screen. I do want to do the math in the parentheses. So Y equals 10 times 1.6 to the T power. And so I've come up with an exponential model that fits the data in the chart. Let's take a look at our second example. So again, it tells us to decide if we should use linear or exponential. So again, I want to look at how the data is changing. So I take on my calculator 528 minus 576. And so from the first one to the second one, there is actually a drop off of 48. Okay, so let's look at these next two. So on my calculator, 480 minus 522. Again, I got a drop off of 48. So seeing that change being the same, that right away makes me think this is probably linear, but those are my y values because that's my second column. So I do have to look at what's happening with my x values. Are they changing by the same amount as well? So 0 to 16, I can see that that is an increase of 16. And then 16 to 32. So again, I always do the new minus the old. So 32 minus 16. And I do get a change there of positive 16 as well. So y and x are both changing by the same amount. And so we do see a constant rate of change. And we could have checked more of these, but we don't often have to. We see it starts out constant. We're expecting it to continue to be constant. And constant rate of change is that iconic detail that makes it linear. So this is indeed linear. That means that I need to write a y equals mx plus b type of formula. And in that formula, I need the start and the rate of change. So the start always happens when time is 0. In this case, time is the age. So this 576 is the start. Now, from there, I need to get the rate of change, which is a synonym for slope. And we know the slope formula. So the slope formula is y2 minus y1 over x2 minus x1. And so our x1, y1, all these things are right here in our table. So 0 would be our x1, 16 is our x2. Did say that right. And this is our y1, this is our y2, because it's our second piece of data, all that. So I'm going to take 528 minus 576. And on the bottom, I'm going to take 16 minus 0. And I get negative 48 over 16. And if I divide that out, I get negative 3. So coming back up here, I can fill that in. Y equals negative 3x plus 576. So the sign legibility distance, I'm guessing that's in feet, but I'm not sure. It doesn't actually say. Looks like it is going down by 3 feet a year. And so as we age for 16 years, because the data in the table is going up by 16s, we have that drop of 48. And so we've come up with an equation that models this. So what we want to do with data is that we want to look for a constant rate of change. And if you find it, so if there is a constant rate of change, if that answer is yes, then that's going to be linear. And if that answer is no, then you have a good case for exponential. You want to check it out by looking at the percentage. But I always start with just the subtraction because that's the easiest one. And so that tells me, yes, it's linear, or it rules out linear, and I can go with exponential. So this is the last of our videos in this content guide. And as we think back through the videos, we first looked at word problems where we're looking for keywords. Second, we looked at the information on a graph where we're looking for, is it a straight line or a curve? And then finally, we looked at data and we're looking for, is there constant rate of change or not? And if it's not, then we want to check out whether or not it's a constant percent of change.